Greetings all, and welcome back. We're talking now about autonomous first-order differential equations. We discussed a few of their properties in the past. Remember, an autonomous differential equation in its relatively general form here, y prime equals typically a function of the independent variable time and the dependent variable y, the mathematical model, the unknown function. Let's suppose in the case that t does not show up in the right-hand side, then the right-hand side is just a function of y alone. We call such a thing an autonomous differential equation. So suppose we have an autonomous differential equation. Today I want to talk about whether or not we can solve the differential equation. There are certain solutions that are of particular import to us. And those are called equilibria. So suppose we have such a thing. Then any point y star in R, where f of y star equals 0, okay. So in other words, if I take a particular value, my dependent variable, and I wind up evaluating to 0 on this point, then it's obvious that y prime is 0 at that point, which means my solution is flat at that point. But if you remember from the slope field, the property of a slope field of an autonomous differential equation, the isoclines were horizontal. So in other words, as I wander across at the same height y star in my slope field, I always have the same slope. So if it's 0 at one point, it's going to be 0 at all points. Okay, so in that particular case, if this is true, so my solution is 0 at that point. Then I can say that y of t is equivalent to y star. Now I'm using some of my own notation here. Instead of saying y of t equals y star, I want this to be true for all values of time. So I'm just using I'm abusing a bit of notation by using the equivalence relation here. It just means that it's the constant solution. There's not a particular value where it equals y star. It's always equal to y star. So this is the constant solution. Is a solution to the ODE. Okay. And that's always true whenever we have a place where y star, where f of y star is 0, we automatically have a solution there. And this solution has a name. We can call it an equilibrium solution. That has other names too. We might call it a steady state solution. And we might call it a constant solution. But often, at least in differential equations, without regard to any particular application, we call it an equilibrium solution. So that becomes an equilibrium solution. It's defined on all of R. And it's particularly easy to find because it reduces the entire problem to finding the zeros of this function f, this right-hand side f. So even if we couldn't solve the differential equation because it was hopelessly complicated, we can at least find the equilibria. So let's look at an example, just to sort of play around with a particular guy. And I'm going to go back to my logistic equation because I like that one. And again, I want to draw a slope field for this guy. I'm at 0 here, and I'm at 1 here. And the first thing I can notice about this is that here, and I'll call this f of z, here f of z equals 0 when z equals 0 and 1. The nice part about this polynomial is it's already factored. So I know when z is 0 or z is 1, I know that I'm there. So in my slope field, I know for a fact that that particular isocline is all flat. And why don't I put these guys in pink so you can see that it's also flat here and it's flat here. And that's really useful for us. I also know something else. I know that if I choose my z star, which can be any particular vertical height here, if I choose an initial point z which is between 0 and 1, then I know that I have a small positive number. A small positive number times 1 minus a small positive number is a positive number. So I know that between 0 and 1, all of my slope field elements are positive there. I can create my slope field knowing that it's kind of steep there, and it gets less steep here, and it gets less steep here also. And I also know that this guy is the same all the way across, and it's flatter all the way across here, and it's even flatter here because the numbers are getting smaller. And I also know above 1, I know that these guys are coming down. And why do I know that? Because if I take a number small, z, a height here, as a number greater than 1, then I know for a fact that that's a number greater than 1 and positive, that's fine. But 1 minus this guy is negative, so it's automatically the case that it's going to remain negative for anything greater than 1. So all these guys are going to be negative. And if you calculate a few of these, you notice that they get steeper as time goes on here. I know that here I'm also again positive but flatter. And I know when I get down here to negative numbers, I know that I'm also negative here. And if you want to calculate that, try sticking minus 1 into here. This guy is positive, but this guy is negative, so the whole thing is negative. So I'm sitting here as my slope field, as an example of my slope field, with something like this. I have a solution here at z equals 1. I have a solution at z equals 0. I have two equilibria solutions. Z of t is equivalent to 1. Z of t is equivalent to 0. And here, in between equilibria, z primes, I'll put this, the sign of z prime does not change. That means that all the way through here, I know for a fact that z prime is greater than 0, right? Because z prime equals whatever this value is at z, and I know that that's a positive guy. And I know for a fact that up here, z prime is less than 0, because if I stick a large positive number in here, the guy in the parentheses is going to be negative, while the guy outside the parentheses is going to be positive. And if I go down below here, I got something negative here too. And I know that right here, z prime equals 0, and z prime equals 0. And I've got a lot of information going on here. I know something else. I know that because this is a polynomial on the right-hand side, by existence and uniqueness of solutions, I know that solutions exist and are unique everywhere. So that means that solutions never can cross. That means that solutions can never meet. So if I were to follow and find an integral curve for this particular guy, I know that an integral curve that starts between 0 and 1 can never leave that band, can never cross the equilibrium at 1. It can never cross the equilibrium at 0. And if you were to draw some of these curves, you would see that these guys basically do things like this. And this guy comes out that way, and this guy comes out this way. But you don't basically, because of the uniqueness of solutions, everything that starts above 1 can never drop below 1. Everything that starts above 0 but below 1 is stuck in that band. And that's actually useful information. Even if you can't solve the differential equation, you know that your solution, the measure, the size of your dependent variable will never get above a particular equilibrium, or never get below another particular equilibrium. Okay. We also know something else. Between 0 and 1, because z prime is greater than 0, that means that my derivatives of my solutions are always positive. That means that between 0 and 1, all solutions always rise. Now, I can rise forever between 0 and 1 and never actually get above 1. It's perfectly okay. It just means that as I get closer to 1, the rate at which I'm rising has to go to 0 basically, but I can still do that forever. Okay? So there's a lot I can say here. What is what I want to say? What do we know? I'll go over it again in a minute. What we know is that solutions exist and are uniquely defined everywhere. We know this because of existence and uniqueness, and in this particular case, the right-hand side is a polynomial. So not only is f of z continuous everywhere, but its derivative, which is another polynomial, is continuous everywhere. So we know solutions exist and are unique on all of R. We know that the only equilibria are at z equals 0 and z equals 1. And we know this because we know the properties of polynomials, that a polynomial can only have as many zeros as its degree, and this is a quadratic, so it can have at most 2 zeros. It may have none, it may have 1, but it can have at most 2. So since I found 2 that are distinct, it doesn't have any more. But we know something else. If I only wanted to know, if I don't really care about the solutions to this, in fact, I don't care about the solution. This model is something that models population dynamics. So it models the future population based upon this particular setup. Okay, so whatever your initial population is, fine. The long-term population is something you might want to know. You don't really care about what happens in the meantime, as long as the long-term population is steady and not 0. Right? It's always a good thing, right? So the long-term behavior of the solutions in an autonomous differential equation become more important than the actual solutions. What happens as t goes off to infinity? And here we can say a heck of a lot. As a matter of fact, I can say the following. If I'm only interested in the long-term behavior as t goes to infinity of any particular solution, I haven't calculated the solutions. I can, they're in the book, but and we could basically, maybe I'll produce a video where we can actually calculate these, but it's not a simple calculation. Bringing this quadratic to the other side as a separable differential equation, it's going to involve that partial fraction decomposition thing. It's certainly doable, but it's not necessary if all you need to know is the long-term behavior of solutions. So if I need to know just long-term behavior, the limit as t goes to infinity of z of t, I can say a heck of a lot. I can say it's minus infinity if z0, my initial value, is less than 0, because I know that all these solutions always go down forevermore. They can't settle down to something pretty far down there because of the fact that f of z will be negative for all z less than 0. There's no other zeros down there, so it can settle down before it gets to infinity. So this will go off to infinity. I know that it's 0 if z0 equals 0. But look at the slope field. Look at how solutions behave. Look at where every other solution goes. I have an equilibrium at 1, which will stay at 1 forever. Anything that starts with a positive z0 will automatically slowly rise and be asymptotic to 1. It must be. Anything that starts above 1, because f of z for z above 1 is always negative, will have to drop, and it can only drop down to 1 because of the nature of the fact that these slope field lines are always negative. No matter how close I get, they will remain negative. So one conclusion I can draw from this is that this will be 1 as long as z0 is greater than 0. Okay. I didn't solve anything. I did a couple of things here, and I know now, in effect, what every single solution to this differential equation will do in the long run without actually solving it. If this were a population model, then what's down here below 0 for an initial population doesn't make any sense, right? So if I start with a 0 population, I'll remain a 0 population. Things just don't spontaneously come into being. Life doesn't do that. However, the interesting thing about this is if I start with a small initial population, then I know long term I will asymptote to something steady in state. Maybe z equals 1 as an equilibrium corresponds to 1 million inhabitants, if it's fish in a pond or something like that. I also know that if I start with too large an initial population, I will have an immediate die-off, but it will stabilize to 1, which eventually is a good thing, modulo the die-off. Anyway, so all this can be gleaned from a knowledge of just bits of information like the Equilibria solution, and a knowledge of the fact that solutions do exist and are unique, that we can start to say a lot about how all solutions behave just by knowing some of the properties of equilibria, the fact where they are and what happens around them. There's a way to classify what happens around equilibrium, but we'll do that in another video. So for now, thank you very much for listening, and we will speak again very, very soon.